Partial discharge merupakan fenomena peluahan muatan elektrik yang bisa menjembatani sistem isolasi baik secara sebagian maupun menyeluruh di dalam suatu bahan dielektrik. Fenomena tersebut timbul diakibatkan oleh banyak faktor. Adanya fenomena partial discharge yang terjadi secara terus-menerus akan menimbulkan panas berlebih pada daerah tertentu yang nantinya akan merusak bahan isolasi dan mengarah kepada terjadinya kegagalan sistem. Sebelum semua hal ini terjadi, maka sangat penting dilakukan pendeteksian dan mengidentifikasian awal untuk mencari penyebab terjadinya peluahan di elektrik tersebut. Pada implementasinya, pengukuran partial discharge menggunakan dua buah pendekatan, pengukuran pada frekuensi rendah dan pengukuran pada frekuensi tinggi. Mana yang lebih baik untuk digunakan? Yuk kita simak webinar seriesnya berikut ini. Selamat datang di Rahman Unet yang seperti biasa akan mengulas tentang dunia kelistrikan dan teknologinya. So, kalau kalian ada yang baru nemuin channel ini, tidak perlu ragu, silahkan subscribe dan aktifkan tombol notifikasinya agar channel ini dapat terus berkembang serta menyajikan konten-konten menarik lainnya. Dan pada video kali ini, kami akan mengulas tentang pengukuran online partial discharge pada starter generator yang akan disampaikan oleh Roger Haslimeyer dalam webinar series.
Please, just to understand, I will jump some slides which I personally think for this topic are not really needed to cross. So first of all, we need to understand, hold on, it's not loading as it should. Okay. We need to understand how our insulation material is built up. So we have a stator, like here on the left side, we can see from a turbo generator, or here now the details we have here in gray or point I, the stator. We have two bars, an upper layer and a lower layer bar, and we have here the slot part where we talk about slot corona protection. Then we have the main insulation, and we can see here the insulation, usually often used as a mica tape, is put around the conductor. So we have a conductor, a single conductor insulation, and the whole main insulation. Here another side cut from a typical design. On top of it, we have the wedge which keeps both parts in the slot. So in order to see what is partial discharge and to understand what it's going, we will explain what are the typical defects what we can have in such an insulation system, and then we can see what happens when these signals going out and how we can measure them. For larger machines, we might have water cooling. This will cause that we have little tubes inside of our bars, which will transport the cooling water from external to internal to the machine, and then back to outside for cooling. When we look at the machine, we can see them, for example, here, these water pipes where the water is put outside. Of course, we can also have hydrogen cooled machines for very large machines in order to increase the cooling efficiency. So we can have air-cooled machines, hydrogen-cooled machines, water-cooled machines, or water and hydrogen-cooled together. On large hydro generators, the principle is the same. The winding is just a little bit more complex. Here, for example, on the top, we can see on a large 20-meter diameter hydro generator stator. But the principle, the two bars per slot, slot corona protection and end winding part is still the same principle. So what kind of defects we might face? Typically, so first at the top right, we have the highest electrical field due to the sharp corner of the copper. Therefore, here we have the highest electrical stress. We might have delamination. Delamination is a detachment between the insulation material which is put around the conductor towards the main insulation. This is a typical effect what we can see when the machine gets older and we had a lot of starts and stops. So whenever we have thermal expansions through to a high temperature, then stopping the machine cools down, we have a sharing effect. And with a long aging, we get a detachment here between the two insulation systems. Of course, we might have also broken conductors. That might happen. We might have a delamination of the main insulation. This is the same due to a lot of starts and stops and high temperature changes. We might have electrical treeing. This is a typical electrical aging effect. And we also might have a problem in the aeration of the slot corona protection. And last but not least, we also might face some air bubbles in voids. These typically are created during a manufacturing process. So this is in the slot part. When we talk about the end winding part, of course, we might have problems in the cooling ducts, separation of the insulation layers in the bending area. Remember the picture, we have this tape which is put around the conductors. So whenever I tape around the bars, I have a technical challenge. Here on the inside, I lose less material than the outside. This could come from the manufacturing process. We may have surface contamination, especially for air-cooled machines, where we might face dust and other deposits on the end winding. And due to electromagnetic forces with ongoing time, we also might have problems in the phase separation or in the bar separation while we get loose of the end winding fixing and the spacers. So I skip now here a bit of the presentations, and I want to go here what's the real effect is. So here, for example, some pictures of air inclusions, electrical treeing, where we get here some air inclusions inside the insulation materials. Here we also can see that on the bottom right picture. So when you see the defects we have, generally what is going on is we have an air inclusion inside of a solid insulator. So because we have an AC voltage, and as soon as the AC voltage is generated, we have basically a separation of the electrons and the ions inside this air inclusion. So imagine we have a 50 or 60 hertz sine wave voltage. So we have a voltage which increases, the electrons and the ions separating through the normal electron flow process. And as long the voltage increasing, the separation is going on. At one point we reach that on this surface more charges are present than the rest of the gas can keep, and we are getting a discharge. So the discharge is not between the two electrodes, it's a discharge within this air bubble or air inclusion, and therefore it's called a partial discharge. That's where the name comes from. That process repeats as long the voltage changes, stops when we reach the maximum, and restarts as soon as we have reached a certain change of voltage again in the other polarity. That's why typically we get partial discharge signs aligned to the applied voltage. These discharges are tiny little current pulses, so high frequency current pulses in a range of a few nanoseconds rise times, and in magnitudes between a few hundred microamps till milliamps. So basically what we have a very high frequency spectrum, as we can see here. So now with these discharges we can acquire with the system, and what we do is we do a statistical analysis of when these discharges happened, how strong they were, and how often. So for the statistical analysis, we create a so-called phase-resolved partial discharge pattern, as here shown. So each dot means one discharge. So we have the phase angle, when they occurred, the magnitude, and the color shows how often. So basically what we have is we get a cluster, a color image, and depending on how the defect is, that statistical analysis looks different. Here, for example, on the top left, slot discharges typically represent themselves as sharp triangle forms with the starting of the discharges around 0, often on machines with a higher voltage range. The start starts earlier of the 0, and for smaller machines like 6 kV or 10 kV machines often start right after the 0 crossing. End winding discharges, also discharges from outside of the machine, often have an accumulation of discharges toward the maximum. And of course, we also can have both types of discharges in the same machine, then we get them overlaid. So how can we measure these discharges, or specifically these high-frequency pulses? So first of all, we need a sensor to separate the high voltage from the high-frequency signal. So high-frequency signal is the discharges, the partial discharges, and the high voltage is the generated voltage you use for generating the energy. Of course, the design of the sensor must respect the overall machine operation condition, like temperature and overvoltages. Also, the design, of course, must withstand the magnetic fields, because we are somehow going to install the sensor close to the stator. But in principle, what do we need? We need to have a high-pass filter with a suitable frequency range to measure the very fast current transients, or these partial discharges. So basically, a coupling capacitor consists of two parts. The first part is the high voltage capacitor itself. The second part is the so-called quadrupole or measurement shunt, and both together create a coupling capacitor. So depending on the different vendors of coupling capacitors, like we as Sparks, we have all these two parts in the same element. So we have here on top, on the brown part, we have the high voltage capacitor. In the aluminium mounting foot, we have the quadrupole where we measure the pulses. So basically what you have is the PD pulse goes through. It's a high frequency signal. The capacitor is a low impedance, so the high frequency signal will pass through the capacitor and will create a voltage drop around the measurement shunt, and that voltage drop, the dot acquisition will measure. So typically coupling capacitors are installed directly at the phase exits. That's the most common way. In hydro generators, some of the vendors install coupling capacitor inside the winding, and some partial discharge monitoring system suppliers install multiple couplers as they use them, for example, for noise separation. So As I said, a coupling capacitor consists of a capacitor and a quadrupole. But how big should be the capacitor? And what size should have the quadrupole? The international standard, IEC 6270, doesn't define that. So there's a full free choice of these two elements in regards to the manufacturers. So unfortunately, often the purchasers define only the capacitors. So they only define one element. But generally, what they should specify is a frequency range, because the frequency range is defined by both elements. So the frequency range of the coupling capacitor is defined by the capacitor and the quadrupole. And the impedance of the quadrupole must match of the used acquisition system, because the acquisition system has also resistance, and if you connect your instrument, both the quadrupole and the input resistance of the instrument will come together. So it might be that when you connect a system, you will change the total frequency range of the system just by connecting an impedance parallel to the quadrupole. So our coupling capacitor, in the quadrupole, we have some special design. We have here a so-called virtual grounding capacitor. This is because when we install the coupling capacitors in a very strong magnetic field, and we are connecting the ground of the signal cable at one side of the shield of the signal cable at the coupler side to ground, and on the instrument side to ground, we get a loop. So we get a one-turn transformer by our installation. And we risk that we create eddy currents in the shield of the coaxial cable or of the signal cable. That's why we are having here virtual grounding. So that means the signal cable is grounded through a capacitor and centrally grounded at the junction box. So our coupling capacitors, we are using generally 1000 picofarad coupling capacitors. Of course, we can also offer other types. Our system is designed for low frequency measurements. Low frequency measurements means our frequency range of the coupling capacitor starts around 100 kilohertz and is open to the upper frequency range. When we look different vendors, different combinations of coupling capacitors and measurement impedances, you can see here on this table the different effects. So for example, if I take 80 picofarad and 100 kilo ohms, I can also get a very low frequency range. The problem is with 100 kilo ohms, you have very high impedance, and that doesn't work with high frequency signals because otherwise we get a lot of noise. We can increase the capacitor and lower the resistance, and then we get to the frequency range what I just showed before. And if I use, for example, a typical high frequency system, which usually measures about 20, 30, 40 megahertz, here, for example, I use 80 picofarad and 50 ohms, I have a frequency range starting from 40 megahertz. So by choosing the coupling capacitor and its quadrupole, you define the frequency range you want to measure. So you have always the possibility, whenever you use a sensor which is able to measure in the lower frequency, you can always cut with the instrument and dedicated filters, cut the lower frequency range to improve the measurement system. But when you use a sensor which already has everything cut, then you might have a problem that you won't see all the PD. Another advantage using a larger capacitance is the output signal. As as bigger the coupling capacitance is, as more signal you're getting out. So when you use a too small capacitor, your output signal is smaller. Consequently, if you have a very low PD level, you would need to amplify the signal to get something out from the coupling capacitor. But when you amplify a signal, you also amplify the noise. When you use a sensor which provides already a large signal, you can always attenuate. Attenuation is always much simpler than amplify. So generally what we can say, higher capacitance values provide a higher sensitivity. Using lower capacitance requires amplifying the signal. That's what I just explained. And when you use lower impedances of the quadrupole, you also might be more sensitive to noise. I skip here. Also, we can also measure with partial discharge with high frequency current transformers that's typically used for cables or for motors. On the market, some vendors say you can measure the RTDs as sensors. I can say you can use that as an additional information, but unfortunately these sensors do not provide a very high sensitivity. So what frequency range we should use? When we look in our standard, the standard doesn't say anything. The standard just says what is the advantage and disadvantage measuring in one or the other frequency range. We have put a summary from the IEC standard. The IEC standard is for rotating machine is the 6003427-2. This is online partial discharge measurements on rotating machines. So they basically make 4 categories. They talk about low frequency range, high frequency range, very high frequency range, and the ultra high frequency range. So what we can say is in the low frequency range, we have a very good sensitivity and we have a wide coverage of the generator winding. But the disadvantage is we can have subjected to noise and disturbances. What does it mean, wide coverage of generator winding? I will come in the next slides. If we go a little bit higher, let's say from 3 megahertz to 30 megahertz, we still have a good sensitivity, and we have another advantage is we have a lower chance of noise and disturbances. When we go from the 30 megahertz to 300 megahertz, so in the very high frequency range, one big advantage is we have low chance of noise and disturbances. But a big disadvantage is we have only high sensitivity close to the sensor location. So basically what we can say is when you choose on the market an 80 picofarad coupling capacitor set, you aim to measure in the C part. When you choose to measure with 1000 picofarad coupling capacitors, you aim for A and B part. So what is now the advantage and the disadvantage while using the different frequency ranges? So let's see what happens when we have partial discharges. So from my initial part of the presentation, I introduced that we have bubbles, air inclusions in the insulation material. So we know we have these bars sitting in the slots, and all these bars are connected in series to each other. So basically what we can do is we can fold up the generator winding and say, here's the generator output. There's a bar going in a slot, coming out into the end winding. It's joined to a next bar, which goes into the slot, and so on and so on. So we have a whole chain. So we can build an electrical equivalent circuit diagram and see where are our impedances. So basically the copper, what we have here in the middle, has a resistance and has somehow an inductance. And we have an insulation material, well, that's this mica tape with epoxy resin. This is a capacitance. So what kind of element that it creates? The stator itself creates an RLC, mainly as a RC, acting as a low-pass filter. So we have partial discharge signal is a very high frequency signal, and a fast impulse, in theory a direct Dirac impulse, has all kind of frequency. So the generator winding, as you said, is acting as a low-pass filter. So we want to measure high-frequency signal, but the machine acts as a low-pass filter, filtering all the signals, the high-frequency signals, away. So that's why generally what we get is at the original source of the PD, we have all kind of frequencies. But because we cannot install the coupling capacitor directly at the defect, we have to install it outside of the machine. This signal will travel through the machine and loses its high frequency content while traveling through the machine. As a simple example, we put two conditions. So we look what happens with low frequency signals and what happens with high frequency signals. It doesn't matter the number now, just that you get a better feeling what happens with low and high frequency signals. So when we look at the low frequency components, so we have our PD source somewhere in the machine. We don't know if it's the end bar, if it's the bar number 5, if it's the bar number 10, no idea. So in the low frequency part, what do we have? Inductances, also series resistance, and the inductance is low in high frequency, and the impedance of the capacitors, that's the insulation material, is high. So the high frequency part is still going through very well. Okay, the low frequency part is going well through very well, and we only have a few losses. But what happens with the high frequency components? In high frequency, the inductance in resistance is high and the capacitance is low. So high frequency parts like to leave through the insulation material, and a lot of losses we have. So the high frequency part only a little bit comes out. So this is a typical characteristic of a low pass filter. So at the end, what we can say, coming back to our electrical equivalent circuit diagram, so we have a defect. We, as a user, we don't know where it is. We can assume it might be here or it might be there. The only thing what we know is we have our coupling capacitor installed at the exit of the generator. So we measure 1 volt, for example, or 100 millivolt. But we don't know, is it the 100 millivolt because it's close and it's small, or originally it was very big and it has been attenuated while traveling through the winding. So in order to avoid this effect, we can say when we measure in the low frequency range, let's say starting from 100 kilohertz, we have much less this effect than when we measure only in the high frequency range. So when you choose a coupling capacitor in one way or the other, you directly influence the measurement results. We say when you use a coupling capacitor who offers from the very low frequency range till the very high frequency range, you can always filter with the instrument. But when you use a sensor which is only measuring in the high frequency range, you may risk that you only see partial discharges which are close to the sensor, because the discharges further inside the machine will never arrive, or will arrive so small that they cannot be detected with the system. So that's the statement. if we measure in a too high frequency range, we lose the original magnitude information. So we don't know if we measure a small PD magnitude because it's close to our coupler, or it's too small because it was far away and has been attenuated through the low pass filter characteristics of the winding. So generally, this is why the generator manufacturers, because it can be Siemens, can be Alstom, or now GE, Andritz, and so on, they use generally systems in the low frequency range, unless the customer specifies a specific vendor, and then, of course, the generator manufacturer sells the system which is required. So this is now theory. You can believe me or not. I show you here a practical example, because it was also our interest to see, is this really true, what we are saying? So for that, we use a small generator bar here, length about 1.8 meter. So what do? We take two coupling capacitors. We take here our 1000 picofarad coupling capacitor, and here in red is an 80 picofarad coupling capacitor. We use a partial discharge monitoring system, which offers a full frequency range, and we use a pulse generator. A pulse generator which simulates or generates partial discharge like signals. Excuse me. So first of all, we connect both sensors at the point of, we call them calibration, or a pulse generator connection, and we calibrate the system, telling the system this is now, for example, 10 nanocoulombs. On the next step, we keep the pulse generator still on the same side, but we move the coupling capacitors to the other side and see how much signal arrives at the other side of the bar. What you can see here, this copper tape here on the slot corona protection, this is to simulate the stator. So, moving the coupling capacitor, the 1000 picofarad coupling capacitor from one side to the other, caused that on the other side we measured 9.7 nanocoulomb. So we lost 0.3 nanocoulomb, so roughly about 3% of the signal over one bar. When we look the effect from the 80 picofarad with the 50 ohm combination input measurement impedance, we measured only 7.5 nanocoulomb. So we had 25% of the signal lost. So now this is only a bar of roughly about 1.8 meter. Especially large turbo generators, which might have 4, 5, 6, 7, or 8 meter stator bar length, this effect will be much larger. So probably after one bar, only about 25 or less of percent of the signal will arrive. That means on the second bar, you have again the same loss. Technically, you can say if you measure in the too high frequency range, you will not be able to measure after the third or fourth bar any kind of PD. The additional effect, what we saw, is the magnitude we can measure. So gain is in our system the amplifying factor. So in with a 1000 picofarad coupling capacitor, we had an amplification of 10. With the 80 picofarad coupling capacitor, we had the amplification of 19. So the same PD source had to be amplified much more to get the same result. So this is an example what we did in ourselves in our laboratory. So there are other publications, for example, this one. Okay, they didn't use nanocoulombs, they used simple volts. So they used volt generator, measured at one, calibrated the system at one side. They had 950 millivolts in both polarities. And after one bar, only 120 millivolts. So in their tests, they had an attenuation of factor 8 between one side of the bar to the other side. Then some results in regards to the sensitivity. So we use same sensitivity on the instrument, just changing the coupling capacitors as a measurement in the laboratory. 80 picofarad gave a very small signal. 1000 picofarad, you can see a very large signal. So same PD source, just using a different coupling capacitor will directly give you a higher result. On the same PD source in a generator, here in this example, having two coupling capacitors installed, obviously the same defect, same measurement sensitivity. With the 80 picofarad, almost nothing to see. Here in this example, I used the 500 picofarad, so fairly bigger, and there's PD visible. So the PD hasn't changed. Just by you choosing the right sensor, you're able to measure much more or much better partial discharges. Of course, in hydro generators, sometimes that can be beneficial, because when you say I can install sensors inside the winding, you remember that picture in the beginning of my presentation with a 20-meter diameter generator, you have plenty of space to install coupling capacitors. So you can install many coupling capacitors, 12, 15, 20, as much you want, and you use the effect of the attenuation. And here, for example, we can clearly see there are some discharges present at one coupler, and as you go away, they're disappearing. Let's say, for example, this type of discharge. Okay, here discharge is present, same phase. Here still a little bit present. Here fully disappear. The same here on the top. Okay, that looks like the discharges are somehow in between these two sensors. But the sensor on the very left side of the winding or the very right side of the winding can't see that at all, or just very tiny. So it can be beneficial for some type of machines. In the summary I showed you in regards of advantages and disadvantages, one of the disadvantages measuring in a lower frequency range is the disturbances and the noise. So, of course, we have a system which can choose the frequency range. You can optimize the measurement range. So, for example, here in this example, when we measure on the very low frequency range, okay, we can see here these vertical lines. These vertical lines, they are coming from the excitation systems, typically from larger machines above 30 megawatts. This is coming from the exciter. That's when the thyristors are firing, used for generating the DC voltage of the excitation voltage and current. So whenever we increase the frequency, you can see the noise disappears, but also the PD disappears. Okay, so it needs a bit the compromise of which frequency range can we use to get the best signal to noise ratio. As I said, when we have a sensor who provides all the signals, the instrument can filter and pick out the signal what has the best signal to noise ratio. If you have a sensor who limits all these parts, we probably only can see this part or even less. So we lose a lot of information by choosing the wrong type of sensor. In our instruments, we have different noise suppression techniques in order to achieve the best signal to noise ratio. So here are some examples. They are mainly from turbo generators. So we see here in the, let's say in the middle, I can filter. As I said, I can choose the right frequency range. Here, for example, we measured from 100 kilohertz to 5 megahertz. We can see here the vertical lines, and here clearly the PD. So by increasing the frequency range from 1 megahertz to 5 megahertz, so only increasing the high pass filter, we have totally removed the noise. Of course, we can see slightly also the PD reduced, but just a little bit. Therefore, this is a good compromise. We have totally removed the noise and we still are able to measure in the lower frequency range. The systems also have a so-called gating. The gating is the system have an additional channel to acquire the noise. So whenever we can measure the noise with this separate noise gate cancelling channel, this noise can be measured and then it is removed. With a big advantage, we do not lose any magnitude information. Of course, we need to find the right spot to measure the noise. This is then another challenge. And one part of our instruments do have so-called the common mode rejection. Common mode rejection, I explain you later on. Basically what it is, noise is present on all three phases at the same time. By acquiring simultaneously all the data, the system is able to reject all signals which are common. So partial discharges are always only between two phases or phase to ground. They never can exist at the three phases at the same time. Therefore, we can use this technology to reject common signals and therefore eliminate the noise. Here, for example, how does this show as an additional analysis? So we have the three phases. We clearly can see from the PD patterns that we have dominant PD activity between phase 1 and 2. And what we are doing is we are calculating how common these signals are. And then we can see, these discharges are between those two phases. That must be a discharge between the two phases. Typically, that can present from here. So how does this calculation works? Basically very simple. We have three phases. We take a polar diagram and we say phase U is at 0 degree, phase 2 is at 120 degrees, and phase 3 is in 240 degrees. We have a discharge pulse simultaneously acquired on the three phases. And then we can add these vectors, make a summary vector, and once the summary vector falls back into 0, we know this is a noise because all the three vectors have the same magnitude. Just as an example, here we have noise, very strong. We try to filter, the noise reduced, some PD appeared, but still noise present. And then we reject all common signals here in the middle, and we can see here very small partial discharges. Of course, we have a very small PD magnitude, so a monitoring generally will still be possible like this, but we can see even signals down to about 200 picocoulomb, which is a very, very small partial discharge measurement possibility. This machine is very special. It's from a hydro generator, which uses a frequency converter for the excitation system. Alternative, using the gating on the neutral point, and also here, this is the noise we have removed, and also here we can see the partial discharges. I'd like to make here a break and like to ask if it is clear the benefits of using let's say high capacitance capacitors or low capacitance capacitors, and if you have understood the benefits using the low frequency measurement. Halo?
Yep, yes. Ada pertanyaan dari Pak Roger, Pak
Pak Tri, apakah sudah mengerti penggunaan pada low frekuensi atau high frekuensi gitu? Atau belum?
Oh, mungkin langsung ke Pak Wahidin ya. Pak Wahidin, di copy Pak.
Ya, kalau tadi sih yang saya tangkap ya masing-masing ada kelebihan dan kelebihannya ya, Pak Tri ya. Kalau yang low gimana, yang high gimana. Nah, terus terkait kita kan yang punyanya yang low frekuensi ya, Pak Tri ya. Ini sekalian nanya langsung boleh, Pak?
Iya, silakan Pak.
Oh, ya. Di kita kan pakainya low frekuensi. Tapi dari hasil yang kami dapat ini lumayan cukup random, Pak. Jadi untuk noise-nya ini terlalu banyak gitu, Pak. Nah, apakah ada updatean, Pak, supaya kami memudahkan untuk cukup confident ini pattern mana yang benar-benar PD dari generatornya gitu, Pak.
Oke, jadi saya ulangi, berarti Bapak kan sekarang pengukurannya PD-nya pakai TMS itu ya Pak ya?
Ya,
Terus dengan menggunakan low frekuensi, tapi banyak pattern gitu ya Pak. Jadi Bapak bingung pattern yang benar yang mana sih gitu kan? Yang menampilkan pengukuran yang benar gitu ya Pak ya?
Iya Pak.
Oke, Pak Roger.
Yes.
Roger, yes. The customer asked about they are right now they are using the TMS series, right? Our spark instrument device. Yep. But according them, they have many pattern there on their display, and then they have difficulties to justify which one pattern is the correct one.
Okay.
Yeah.
Yeah, you can share this information with us, and we can help you. Basically, when it stays informal, then we can just answer you by an email. If you want to have a formal analysis report, then it will be charged and cost a few €100 that you have a formal analysis. What you should have in the documentation, I hope you have received the documentation, but otherwise I can send you that again. I can go to the end. In our documentation, here's some examples of what you might face. I don't want to go too much in detail. I can hand over that to you. Just said, the system they have already on site is, let's say, from the older generation, and probably our documentation was not that in deep. So please, I will send you the latest manual, and there might probably then some functions described in the system which are not existing in the version you have. So basically, as I said, I understand evaluating the partial discharges is very difficult, especially for customers who are not very familiar with that and don't do that on a regular basis. For that reason, we have provided in our documentation a catalog of typical PD patterns and their defects, which helps basically to identify the source or the root cause of the partial discharges. I also suggest to the customer to purchase the IEC standard I was referring before in this presentation, because at the end, in the appendix, you also can find a catalog of typical PD patterns which can occur in machines. Unfortunately, we cannot take them because, of course, they have a copyright on it. But the catalog is very interesting, and you get also a very nice and good description about the risks of having such type of PD. So basically, you have a PD pattern. The big advantage is the PD patterns from our systems, or as we use here, and the ones used in the standard are coming all from the same design, from different vendor, but using low frequency measurement system. We all know the company Arispower from Canada. They have a very specific PD pattern design, which doesn't allow you properly analyze the source. As I can say, our PD patterns we are providing are compatible to the examples you can even find in the international standard. So as I said, slot discharges typically are shown with a sharp increase around 0, having a triangle-shaped PD pattern. End winding discharges more towards the maximum. Then, for example, when you have gap-type discharges, this is typically an arcing, which you might have, for example, either from bar to bar due to insufficient spacing. You might find such discharges on the bushing, on the generator bushing. When you have delamination, for example, and you have an arcing between the conductor and the insulation system of the bushing. You might have that at the straight parallel part of the end winding when it's arcing between the two phases. Here in this bottom side was a defect using a wrong coating at the slot exit. So we have here the slot exit bar and the pressure finger arcing between the pressure finger and the bar. Also here making clouds. So whenever you have a cloud type, this is some kind of arcing you have. Then what you can have, if you have PD patterns which have a shape similar than the applied voltage just by having a phase shift, this is typical signs of vibration sparking. Vibration sparking is not really PD, but can be measured with the same low frequency signals. That's why the bar is moving inside of the slot due to insufficient fixing, and that can create an arcing, which totally destroys the slot corona protection. Then, as I said, we have the possibility that we are measuring 3 phase, so we always have to compare the 3 phases, so we can see, do we have discharges at the same time? Then you look at the voltage reference shape to see, is it a phase to ground or phase to phase discharges. So typically phase to phase discharges look like this. Then, for example, air-cooled machine, here this example, okay, we measure, we know now from the catalog, when we have some few discharges towards the maximum, that's more indication towards surface discharges. Surface discharges are typically signs of dirt contamination. In this way, we open the machine, we see it's dirty, we clean the machine, and we perform a measurement afterwards, and all what we can see, oh, that's all gone. Okay, perfectly, we were right. This is surface discharges, and the rest what we have is internal discharges.
Oke, mungkin ini dapat saya share ke sahabat sekalian. Jika ada pertanyaan ataupun koreksi, silahkan tinggalkan pesan pada kolom komentar. Terima kasih sudah menonton, sampai bertemu di webinar series berikutnya.